Good afternoon. Now we will see some questions which are related with your flexural member that we can say beams. So now actually try to understand the difference between axial members and flexural member. In axial member, our load is along the longitudinal axis, and in flexural member, it is perpendicular to the longitudinal axis. So you can see load is perpendicular to the longitudinal axis. And for axial members, which we are going to say as tension compression, load is along longitudinal axis. Longitudinal axis. So this difference you have to keep in mind, that is load is along, I can write, along longitudinal axis, and in beams it is perpendicular to the longitudinal axis. Beam and flexural members and bending moment. So if you remember, we have when we have these loads perpendicular to this, then we are going to draw a shear force diagram, and then we are going to draw bending moment diagram, and beams are designed for these shear force and bending moment values. What is relation between M and MD? Now we are well familiar with this. So we have T, P, and then this M. These are the forces which are developed due to external loads. And then MD, so we can have TD, we have seen PD, and then we have MD. These are the properties of the section. So that is MD is moment of resistance, or we can say design uh, bending strength of the member. So you can see over here design bending strength of the section. So M, and what will be relationship? M should be always less than or equal to MD. That that is strength of the member should be always greater than the load coming on it. And then we have what are the different types of beams. So we have laterally supported beam, laterally unsupported beam. So these classification we have depending upon the compression flange. So compression flange will decide your beam is laterally supported or laterally unsupported. How? So you can see this. If my compression flange is laterally restrained, then we are going to say that beam is laterally supported. So we are not allowing any displacement along a lateral direction of the beam, and if that is satisfied, then my beam is laterally supported. And if my compression flange is allowed to deflect or is not laterally restrained, then beams are known as laterally unsupported beam. So in laterally supported beam, my strength is greater than laterally unsupported beams. Now calculation for MD. Now again this MD we are going to the formula we are going to divide into two parts, which depends upon your value of V. If your value of V is less than zero point 0.6 VD, where VD is the design shear strength, and then second we have greater than zero point 0.6 VD. Now what happens in these two cases? When we have this case, we have to use this formula. You can see design shear force does not exceed zero point 0.6 VD. We are going to use in this one. What will happen in this case? In this case, my moment predominating, moment predominating, and beam is designed for flexure only. Designed for flexure. For flexure. So when we will have less than zero point 0.6 VD, but when it is greater than zero point 0.6 VD, then we have moment and shear both are predominant. Moment and shear both are considerable. Both are predominating, or I can say dominating better way. So here also dominating I can mention. And so this will be combined design for combined design for shear and flexure. Shear and flexure, and therefore we have to go to section 9 in this case. section 9, which is for combined effect. And this we have, you can say 8.2.1.1 means we have, this is section 8, which is for pure bending or for moment dominating. And then if you have greater than zero point 0.6 VD, then you can have this formula MdV, which is given in 9.2. MdV is equal to Md minus beta, Md minus MFD. And this beta again depends upon V, that is V by Vd whole square minus 1. And then by this, we are going to calculate MdV. So if you will see, this will be little or small reduction, I can say, in Md due to this factor. Now this Md we are going to calculate by this formula, and MFD, this we are going to calculate moment of resistance by neglecting shear area, means web we are not considering, neglecting shear area. Now this value 1.2 ZeFy upon gamma MO is we have for simply supported, and 1.5 ZE. So this value we can say this should be uh, less than or equal to 1.2 ZeFy upon gamma MO, that is for simply supported, and 1.5 ZeFy upon gamma MO, that is for cantilever. So my value should be less than or equal to these values which we are going to say over here. So now why this value? Because generally your value of ZP, this is less than or equal to 1 sorry, ZP we have, or I can say ZP, this will be greater than or equal to, I will say, ZE. And we have ZP maximum value, that is 1.2 ZE. And therefore this is considered as 1.2 actually. Then what is formula for shear strength? So you can go to a 8.4.1, the nominal plastic shear resistance Vn equal to Vp, and Vp we have AVFyW upon root 3, and Vd is Vn upon gamma MO, and Vn is Vp. So if I will write Vd, then we have AVFyW upon root 3 gamma MO. This is my formula for Vd. Combination of Vn and Vp, that all we are going to consider, and we can write this formula directly. What is formula for shear area? So AV we have over here, and that we have depends upon your rolled section and welded section. So in 8.4.1.1, so value of AV that is mentioned here, shear area. So H into D TW, which is for rolled section, and D into TW, which is for welded section. So in hot rolled section, we are going to consider overall depth, including flange, and in welded connection we are going to consider depth of web only, depth of web. So that is the difference between the two. Then we have what is beta B for semi compact section. So we have ZE upon ZP, and therefore your value of MD becomes ZEFY upon gamma MO for semi compact section, for semi-compact. Why? Because we have formula beta B ZP Fy upon gamma MO. If we will put ZP as ZE divided by ZP into ZP Fy upon gamma MO, and your ZP gets cancelled, and you will get ZE Fy upon gamma MO for semi-compact. But for compact, compact and plastic section, my value of beta B is equal to 1. So these are the some questions which are related with your flexural member. Then again we will go one video on this flexural member questions. So